All right, we're going to cover two sections, production and properties of E&M waves. Those are section 2110 and 2112. Let's share the PowerPoint and continue on. Okay, if the current in an LC circuit alternates rapidly, the circuit loses some of its energy in the form of electromagnetic waves. In fact, electromagnetic waves are radiated by any circuit carrying an alternating current. The fundamental mechanism responsible for this radiation is the acceleration of a charged particle. Whenever a charged particle accelerates, it radiates energy. Let me repeat that. Whenever a charged particle accelerates, it radiates energy. When an alternating voltage is applied to the wires of an antenna, electric charges in the antenna are forced to oscillate. This technique is the source of the radio waves emitted by the broadcast antenna of a radio station. The figures here show the production of an electromagnetic wave by oscillating electric charges in an antenna. Two metal rods are connected to an AC source, which causes charges to oscillate between the rods. The output voltage of the generator is sinusoidal. At t equals 0, the upper rod is given a maximum positive charge and the bottom rod an equal negative charge, as in figure A. The electric field near the antenna at this instant is also shown. That's the little orange E arrow right next to the antenna. As the charges oscillate, the rods become less charged. The field near the rods decrease in strength, and the downward directed maximum electric field produced at t equals 0 moves away from the rod. When the charges are neutralized after an interval equal to 1/4 of the period of oscillation, as in figure B, the electric field has dropped to 0. This continues, and after a half period of the field, the field is pointing up, as in figure C. These oscillations continue as indicated in figure D. Note that the electric field near the antenna oscillates in phase with the charge distribution. The field points down when the upper rod is positive and up when the upper rod is negative. Also, the magnitude of the field at any instant depends on the amount of charge in the rods at that instant. As the charges continue to oscillate and accelerate between the rods, the electric field is set up by the charges moving away from the antenna in all directions at the speed of light. Because the oscillating charges create a current in the rods, a magnetic field is also generated when the current in the rods is upward, as shown in the figure. The magnetic field lines circle the antenna. We call the right-hand rule number 2, like that, and are perpendicular to the electric field at all points. As the current changes with time, the magnetic field lines spread out from the antenna. Far from the antenna, the strengths of the electric and magnetic fields become very weak. Note that, number 1, a changing magnetic field produces an electric field, and number 2, a changing electric field produces a magnetic field, as predicted by Maxwell. Okay, we're going to continue on with properties of electromagnetic waves. These induced electric and magnetic fields are in phase at any point. They are in phase. At any point, the two fields reach their maximum values at the same instant. This synchrony is shown at one instant in time in the figure. Notice that the E and B fields are perpendicular to each other, and both fields are perpendicular to the direction of motion of the wave. The second property is characteristic of transverse waves. You can see that an electromagnetic wave is a transverse wave. An E&M wave can also be thought of as a plane wave. A plane electromagnetic wave is a wave traveling from a very distant source. Notice in the figure, the electric field is in the Y direction and the magnetic field is in the Z direction. Light propagates in a direction perpendicular to these two fields. That direction is determined by yet another right-hand rule. Number one, point the fingers in your right hand in the direction of E. Curl them in the direction of B. The right thumb then points in the direction of propagation of the wave. So this is E, this is B, and that's the direction of the wave. Okay, let's go back to the share. Electromagnetic waves travel with the speed of light. In fact, it can be shown that the speed of an electromagnetic wave is related to the permeability and permittivity of the medium through which it travels. Maxwell found this relationship for free space to be the one shown here, where c is the speed of light, mu sub 0 is the permeability constant of vacuum, and E sub 0 is the permittivity of free space. Substituting these values, we can calculate the speed of light. Which is about 3 times 10 to the 8th meters per second. Because electromagnetic waves travel at the same speed as light in vacuum, scientists correctly concluded that light is an electromagnetic wave. Maxwell also proved that the ratio of the magnitude of the electric field to the magnitude of the magnetic field equals the speed of light. That is, E over B equals C. Pretty amazing. Electromagnetic waves carry energy as they travel through space, and this energy can be transferred to objects placed in their paths. The average rate at which energy passes through an area perpendicular to the direction of travel of a wave, or the average power per unit area, is called the intensity I of the wave, and is given by the relationship shown here, where E max and B max are the maximum values of E and B. The quantity I is analogous to the intensity of sound waves. From the relationship among E, B, and C, we can write this relationship. EB equals E divided by B equals C, so E max equals C times B max. That is B max, which is equal to, E is equal to B max divided by the square root of mu sub 0 and E sub 0. Okay, that means we can express the intensity as shown here. I equals E max divided by 2 mu sub 0 C, which is equal to C over 2 mu sub 0 times B max squared. Note that these expressions we use are average power per unit area. A detailed analysis would show that the energy carried by an electromagnetic wave is shared equally by the electric and magnetic fields. When E and M waves strike an area A of an object's surface for a given time delta t, energy is transferred to the surface according to the relationship shown. Momentum is also transferred. That means when an E and M wave hits a surface, pressure is exerted on it. Oops, jumped the gun. Let's assume here that the electromagnetic wave transports a total energy mu to a surface in a time delta t. If the surface absorbs all of the incident energy u in this time, Maxwell showed that the total momentum delivered to this surface has the magnitude here. Momentum equals mu over c. If this surface is a perfect reflector, then the momentum transferred in a time delta t for a normal incidence is twice this. This is analogous to a molecule of gas bouncing off the wall of a container in a perfectly elastic collision. If the molecule is initially traveling in the positive x direction at velocity v, and after the collision is traveling in the negative x direction at velocity 2v, its change in momentum is 2mv. Change in momentum equals mv minus mv, which is 2mv. Light bouncing off a perfect reflector is a similar process. So for complete reflection, The momentum is shown here. The momentum is 2u over c. So for complete absorption, we get u over c. For complete reflection, we get 2u over c. Okay, this figure is an apparatus for measuring the radiation pressure of light. In practice, the system is contained in a high vacuum. Although radiation pressures are very small, about 5 times 10 to the minus 6 newtons per meter squared for direct sunlight, they have been measured with a device like the one shown here. Light is allowed to strike a mirror and a black disc that are connected to each other by a horizontal bar suspended from a fine fiber. Light striking the black disc is completely absorbed, so all the momentum of the light is transferred to the disc. Light striking the mirror head-on is totally reflected, so the momentum transferred to the mirror is twice that transmitted to the disc. As a result, the horizontal bar supporting the disc twists counterclockwise as seen from above. The bar comes to equilibrium at some angle under the action of the torques caused by the radiation pressure and the twisting of the fiber. The radiation pressure can be determined by measuring the angle at which equilibrium occurs. The apparatus must be placed in a high vacuum to eliminate the effects of air currents. It's interesting that similar experiments demonstrate that electromagnetic waves carry angular momentum as well. So let's summarize the properties of electromagnetic waves, and this is an important slide. Number one, electromagnetic waves travel at the speed of light. Number two, electromagnetic waves are transverse waves because the electric and magnetic fields are perpendicular to the direction of propagation of the wave to each other. Number three, the ratio of the electric field to the magnetic field in an electromagnetic wave equals the speed of light. And number four, electromagnetic waves carry both energy and momentum, which can be delivered to a surface. This ends the properties of E&M waves by the antenna and the antenna section. The next section we'll discuss will be 2112, the spectrum of E&M waves.